Good morning, everybody. My presentation today is titled Biomaterials from Aquatic Lyrium, Physicochemical Characterization and Application in the Removal of Pb2. The presence of lead, Pb superscript 2, in water represents a serious environmental and public health issue. This heavy metal is highly toxic even at low concentrations, and prolonged exposure can cause severe neurological, renal, and cardiovascular damage. Various methods have been developed for lead removal from water, including precipitation, ion exchange, membrane filtration, and adsorption. Among these, adsorption stands out for its simplicity, low cost, and high efficiency. Many materials have been investigated as adsorbents, such as clays, zeolites, biochar, and activated carbon. In Mexico, the excessive proliferation of water hyacinth, Eichhornia craspes, in rivers, lakes, and dams has become a significant ecological and economic problem. It obstructs waterways, displaces native species, and increases water loss through evapotranspiration. However, this invasive biomass can be transformed into a low-cost adsorbent. One promising approach is the production of activated carbon from water hyacinth through chemical activation with phosphoric acid, H3PO4, which improves porosity and surface area, enhancing its adsorption capacity from Pb2. The main objective of the study is to evaluate the effectiveness of activated carbon from water hyacinth in removing lead from water, specifically synthesis of activated carbon from Eichhornia craspes through chemical activation using H3PO4, characterization of the textural, structural, and physicochemical properties, evaluation of Pb2 adsorption capacity in aqueous solution at pH 5, preparation of the precursor material. The raw water hyacinth was washed, sun-dried, ground, and sieved with 60 mesh screen. Preliminary carbonization. Dried powder was heated at 300 degrees Celsius for 2 hours under constant N2 flow, 150 milliliters per minute, with a heating rate of 5 degrees Celsius per minute. Chemical impregnation. The carbonized material was mixed with 36% H3PO4 in a 1-to-1 ratio for 12 hours at 25 degrees Celsius, then dried. Chemical activation. The impregnated material was heated at 550 degrees Celsius for 1 hour under constant N2 flow, 150 milliliters per minute, with a heating rate of 5 degrees Celsius per minute. Characterization of activated carbon. Surface physicochemical properties. Active sites and point of zero charge, PHBCC. FTIR spectroscopy. Functional groups and vibration properties. TGA analysis. Thermal behavior. Adsorption experiments. Isotherms. Batch experiments with initial Pb superscript 2 concentration from 50 to 800 milligrams per liter. Data fitted to Langmuir and Freundlich models. Lead quantification. Using a Pb superscript 2 ion selected electrode. Results. Table 1 shows the physicochemical properties of water hyacinth. Derived activated carbon, acely, chemically activated with H3PO4. The zero point of charge, PHBZC, was determined to be 3.22, indicating that the material surface is acidic. This acidity is confirmed by the concentration of acidic sites, 0.47 milliequivalent G superscript 1. In the absence of basic sites, a result directly associated with the chemical activation treatment. Based on the PHBZC value, when the pH of the solution in contact with the carbon is higher than 3.22, the surface acquires a negative charge, which promotes cation attraction. Figure 1a displays the Pb2 adsorption isotherm, where a maximum adsorption capacity of 273.26 milligrams G superscript 1 was achieved. This result indicates that the predominant adsorption mechanism is electrostatic attraction between the carbon rings on the surface and the Pb superscript 2 cation, favored by the negative surface charge of material at pH 5, a value higher than the PHBZC, 3.22. Table 2 presents the fitting parameters of the adsorption isotherm models applied to the experimental Pb2 adsorption data at different concentrations. The R superscript 2 and %D values indicate that the Langmuir model provides the best fit to the experimental data. The good agreement with the Langmuir model suggests a chemisorption process, considering that this model assumes a rate-limiting step involving specific chemical interactions between adsorbate and adsorbent. Figure 1b shows the FTIR spectra of the activated carbon ACWH and the activated carbon after Pb2 adsorption. The band at 2904 cm superscript 1 is assigned to C, H stretching vibrations and alkane groups, while the peak at 1733 cm superscript 1 corresponds to C equals O stretching and carbonyl groups. Additionally, the bands between 1600 to 1500 cm superscript 1 are associated with C equals C stretching vibrations and aromatic rings. The absorptions in the 1000 to 1250 cm superscript 1 region are attributed to C, O or C, O. C stretching in functional groups such as acids, phenols, ethers, and esters, whereas the peak at 1022 cm superscript 1 is related to P, O, P stretching vibrations. Figure 1c shows the thermogravimetric analysis, TGA, where total weight losses of 87% for Eichhornia craspes, 49.7% for the activated carbon, acely, and 70.9% for the activated carbon after Pb2 adsorption were recorded. For E crassipes, the main thermal events correspond to the degradation of cellulose and hemicellulose between 200 to 400 degrees Celsius, followed by lignin decomposition between 400 to 500 degrees Celsius. The activated carbon exhibits two main degradation stages. 1. Loss of residual H3PO4 trapped in the pore structure at approximately 660 degrees Celsius. 2. Structural rearrangement of the carbon matrix above 900 degrees Celsius. After PB2 adsorption, a marked weight loss is observed at 950 degrees Celsius, attributed to the thermal decomposition of precipitated lead oxides and hydroxides on the carbon surface. Combined with the adsorption isotherm results, Figure 1a, which revealed a maximum adsorption capacity of 273.26 milligrams G superscript 1 and a predominant fit to the Langmuir model table 2. These findings suggest that PB2 removal is mainly driven by electrostatic interactions between the negatively charged carbon surface at pH 5, pHZC 3.22, and Pb superscript 2 ions, with chemisorption as a dominant mechanism. The activated carbon obtained from water hyacinth, Icornia crassipes, through H3PO4 activation exhibited an acidic character. pH BZC equals 3.22, and oxygenated and phosphorylated functional groups that favored PB2 adsorption, reaching a maximum capacity of 273.26 milligrams G superscript 1, as fitted to the Langmuir model. FTIR analysis confirmed the presence of C equals O, C, O, C, O, C, and P, O. P groups involved in the process, while thermogravimetric analysis revealed the formation of lead compounds decomposing at around 950 degrees Celsius. These results demonstrate the material's potential as an efficient adsorbent for PB2, removal from contaminated water.